In this video, I want to introduce mainly two programs, satellite programs from NOAA. Okay, the first program is called GOES, the Geostationary Operational Environmental Satellites. It includes three satellites here: GOES 8, GOES 9, and GOES 8, GOES 10, and GOES 12. So sensors, they're all using GOES imager, okay, with 5 bands, 1 visible band, and 4 thermal bands. So you can say this satellite is mainly for weather forecasting. So it doesn't need so many visible bands. So thermal bands, they are main characters on GOES sensors, GOES imagers, okay? And another program is called POSE. The full name is Polar Orbiting Operational Environmental Satellites. It's a very long name, right? Just call it POSE. There are several satellites. That's actually a lot of satellites related to this program. TIROS satellite and NOAA 8 to 18 satellites. The main sensor for POSE, okay, for this program is called AVHRR, which is also very famous in Earth observing satellite family. Okay, its full name is Advanced Very High Resolution Radiometer. Okay, AVHRR is mainly used for mapping vegetation and sea surface characteristics. Okay, land cover characterization and the mapping of daytime and nighttime clouds, snow, ice, and surface temperature of land, and also you could say maritime temperature or ocean surface temperature. Okay, and here is a figure showing you the coverage of two GOES satellites because they are geostationary, which means they are just staying on the Earth stationary orbit, which is the only orbit, right, for Earth stationary satellites. So they are actually covering most part of Pacific Ocean and Atlantic Ocean and North American and South American. Okay, so GOES West satellite is right here. GOES East satellite is here. Like I mentioned before, these two satellites, they were launched by NOAA. The full name is National Oceanic and Atmospheric Administration. It's a administrative agency of U.S. government. Obviously, what they care is weather and climate of U.S. Okay, so it makes sense that these two satellites, they are looking at what? They must include U.S. soil, of course, but they can also cover most part of Pacific Ocean and Atlantic Ocean and North and South America. Okay, so this is a position of this figure is showing you the position of these two satellites. And the AVHRR here on the left side is an illustration of the appearance of AVHRR. Okay, the special part about this satellite is that it has a very short revisit time, which is 1 day. The spatial resolution of this sensor is not that high. It's only 1.1 kilometers by 1.1 kilometers. Okay, but you should know that this sensor is mounted on these satellites, okay, NOAA 8 to 18 and TIROS-N, and different from GOES satellites, AVHRR, and it is on these satellites. And these satellites, they are all what? They're all using sun-synchronous orbits, not geostationary orbit. Okay, which means that these satellites, they can cover the whole Earth's surface instead of a part of the surface. Okay, there is relative movement between these satellites and the Earth. Okay, not like geostationary satellites. They are relatively their relative. There, there is no relative movement between a geostationary satellite and Earth. Okay, because a geostationary satellite rotates with with the same angular speed as the angular speed of the Earth, right? Okay, here is a table showing you the different bands of AVHRR. Okay, and actually five bands, right? Rad, near infrared, mid wave infrared, long wave infrared, and they are different. There are different applications for each band here, and we have band description here, right? Red and near infrared vegetation mapping, NDVI, daytime cloud, snow, and ice, and for different infrared bands, they have different purposes or applications. And here, since we have seen this term here, it's called NDVI. I want to give you an introduction to this index. It's a very simple but effective index, or you can say indicator, invented to address the abundance of vegetation on the surface of the Earth. Okay, so the full name is called Normalized Difference Vegetation Index. So it's a very simple but effective index using the reflectance features of vegetation at red and near infrared bands to address the abundance of vegetation. Okay, how to address this index? Here is the figure. So here we have the reflectance spectrum of vegetation, right? From visible light to infrared. Okay, so of course the horizontal axis here is for spectral wavelengths, and the vertical axis is here for the reflectance of vegetation at different wavelength. Okay, so here what we care is here. Okay, this is red band, and you can see that the reflectance of vegetation at red band is pretty low, which means that vegetation barely reflects red light. Okay, but after that, there is a very huge difference in terms of reflectance at near infrared band. At near infrared band, vegetation has pretty high reflectance, at least compared to red band. This reflectance here is pretty big, and this difference happened in a relatively shorter distance of wavelengths, because red band and near infrared band, they are neighbors to each other, and we can see here is a very steep cliff here from red to near infrared. So this is a very good signature from vegetation. I mentioned before that each reflectance spectrum of an object can be considered as a fingerprint of that object, and this huge jump of reflectance between red and near infrared band is very unique. It happens only on vegetation. So we should be able to use this feature to design an index to differentiate vegetation from other objects on the ground. So that's the purpose of NDVI. How to use this? It's pretty simple. NDVI is a ratio between the difference between the difference between near infrared band and red band, and the sum of near infrared and red bands. Okay, so the difference here, of course, is the difference of reflectance of these two bands. Again, the sum of these two bands also is the reflectance, the sum of reflectance from these two bands. So everything here is surrounding what? Is surrounding this huge difference of reflectance between red band and near infrared band. Okay, so this index is called normalized because actually what this denominator is doing here is creating a baseline, a baseline. Okay, no matter how high your a specific a plant, a specific flower, a specific tree, or specific grass, how high the reflectance of that specific plant at near infrared band, or how low the reflectance of a specific plant at red band, it doesn't matter. I will just sum them and use that sum as the denominator for that specific plant, or for an area of plant. It doesn't matter. And I will use the difference between near infrared band and red band as numerator, and I calculate the ratio of them. And the denominator is actually trying to normalize the difference between near infrared band and red band. Okay, so NIR here is used to address the reflectance at near infrared band. RED here is used to address the reflectance at red band. So if you are using AVHRR, because band 2 of AVHRR is for near infrared band, band 1 of AVHRR is for red band. So you can just simply replace NIR and red with AVHRR band 2 and AVHRR band 1. So this formula here is a very general formula for different sensors. As long as they have near infrared band and red band, you can simply use those corresponding bands to replace NIR and red here. Okay. So the NDVI equation produces values in the range of -1 to +1. So NDVI is always having a value between -1 and somewhere between -1 and +1. So we're increasing the positive values indicating increasing green vegetation. And negative values indicate what? Non-vegetated surface. Okay, so usually we use 0.3 as the threshold to judge if a specific pixel is vegetation or not. So if you calculate the NDVI value for a pixel and its value is larger than 0.3, we say, okay, it's a pixel mainly or fully covered by vegetation. If the NDVI value is smaller than 0.3, then we say, okay, this pixel is not covered, is totally not covered by vegetation, or is barely covered by vegetation. But this threshold here, 0.3, is very arbitrary, which means that depending on specific data you have, depending on specific season of the picture, specific area, latitude, a lot of other factors can affect the setting of the threshold. 0.3 is just a convention, right? Of course, if your NDVI value is even lower than 0, it's pretty sure that this pixel has nothing to do with vegetation. Okay, but above 0.3, the higher the NDVI value, the higher the abundance of vegetation within that pixel. Okay, so NDVI value is calculated by pixel. When you are calculating NDVI value for the whole image using ERDAS, using ENVI, using ArcGIS, or other GIS or remote sensing software, you will, as a result, you will have another remote sensing image for NDVI, which means that in that resulting image, each pixel has a specific value, and that value is not a reflectance or DN value anymore. It is the value for NDVI. So NDVI is for each pixel. Okay, you calculate NDVI by pixel. And the last one sensor here is less famous, is called CVIFS. C-Viewing Wide Field of View Sensor. It's basically for the color of ocean, because the color of the water can reflect a lot of things. Okay, that's part of watercolor remote sensing, and also it can be used to address the surface temperature and other parameters of water body and ocean, especially ocean. Okay, the spatial resolution you can see here is again not very high. It's actually very coarse. It's 1.13 kilometers. You say why? Because when we are trying to observe large scale landscapes, for example, ocean, high spatial resolution is meaningless. We don't need a high spatial resolution for Pacific Ocean, right? It's just a huge amount of water. Why do I need to know to look at this water with a high spatial resolution, for example, 30 by 30 meter? Within 30 by 30 meters square, it's just water, right? So it's not, there is no need to make the spatial resolution of oceanic satellites very high. It's not necessary. Okay, but for other satellites, for example, Landsat satellites, they care about different land cover types, right? In rural areas, in urban areas. And these areas, they are more or less have been invaded by human beings. So there are croplands, there are buildings, there are roads, there are houses, right? Even small cars. So the land cover composition is very complex in especially urban areas, and could be complex in rural areas, but less complex than urban areas. So if you're trying to launch a satellite who cares about actually urban areas and rural areas, such as Landsat satellites, you have to make sure that the spatial resolution is high enough so we can differentiate different land cover types on the ground. For example, a building, if you are looking at a building from the top of it, it could be smaller. I mean, most buildings, they are smaller than 30 meter by 30 meter, right? For example, a house, for example, a small apartment building, right? So high spatial resolution is meaningful, is even crucial to urban areas, but it's not necessary. It's simply not necessary for ocean or for large area of forest or wildland. So yeah, like I mentioned before, spatial resolution is not something that you should consistently pursue. You need to make sure that it is necessary. Okay, then you can pursue that. But if it's not necessary, no need to pursue the spatial resolution. Okay, and the revisit time for this sensor is also very short. It's only 1 day. It has 6 visible bands and 2 near infrared bands. Okay, so this is the content of this video, and in next video, I'm going to introduce multispectral imaging using imaging systems using linear arrays, okay, including spot systems from Europe and very high resolution sensors, right? Here, this resolution here refers to spatial resolution. Okay, I'm going to introduce several very famous, successful commercial satellites: ICONOS, QuickBird, OrbView, and others. Okay, thank you.